Okay, let's unpack this. Think about your smartphone, your smartwatch, even the complex systems in your car. What's the hidden powerhouse making all that magic happen? Chances are it's something called a system on chip, or SoC. It's truly the heart of modern electronics, representing, well, a fundamental shift in how we design circuits.
Yeah, it's fascinating because traditionally, components like the CPU, the GPU, memory, they're all separate pieces on a circuit board. But within SOGO, all of those critical elements, processing units, memory, I/O interfaces, even things like Wi-Fi and Bluetooth, they're all seamlessly integrated onto a single microchip.
Wow.
It's like a complete electronic system just packed into one compact little package.
And these aren't just for phones, are they? I mean, where else are SoCs making a big impact that might surprise you, our listener?
Oh, absolutely, not just phones. So SoCs are, well, they're ubiquitous now. They are the cornerstone of mobile devices, sure, but they also power embedded systems in cars, industrial machinery. And we're seeing them more and more in personal computers and servers, too. They can even be custom-tailored for specific jobs. Those are called ASICs, application-specific integrated circuits. Shows how versatile they are.
So why? Why are these SoCs so indispensable? What makes them the go-to technology across so many different fields?
Well, their widespread adoption really stems from a powerful synergy of advantages. First off, you get significant size and weight reduction, just consolidating all those components.
Right, miniaturization.
Exactly. And that's paramount for those sleek designs in wearables and phones. You get powerful performance without the bulk. Then there's power efficiency. Integrating everything on one piece of silicon dramatically cuts down on the energy needed for data to travel between separate chips.
Which means better battery life.
Definitely extends battery life.
Okay, so less power, smaller size. But what about speed? Does packing it all together help there too?
It absolutely does. That's where performance enhancement comes in. The sheer physical closeness of components within a Zathorohi means lightning-fast communication. Less distance, less delay, or latency.
So things feel more responsive.
Exactly. And from a business angle, they're incredibly cost-effective for mass production. Manufacturing one integrated chip is generally cheaper than making, assembling, and testing lots of separate parts.
Makes sense. And what about reliability? Fewer parts, fewer things to break? Or does putting everything together introduce new problems?
That's a great point. Generally, it leads to higher reliability, fewer individual parts, fewer external connections, just fewer potential points of failure compared to older multi-chip designs.
Oh.
And it actually simplifies the design process for engineers, too. They manage one integrated solution instead of juggling numerous separate components. It's really that physical integration, those shorter electrical paths, that drives everything, the speed, the performance, and the power savings all at once.
So for you, our listener, today's deep dive is all about unraveling the really intricate process behind these tiny powerhouses. We're going to trace the journey from just an idea, a concept, all the way to a tangible piece of silicon. It's like a grand blueprint, a really intricate dance of engineering.
It truly is. And the demand just keeps growing: smaller, faster, more power-efficient devices. That constantly fuels innovation in SoC design, and that innovation unlocks possibilities for, well, new kinds of gadgets and applications we couldn't even imagine before.
So how do we even begin to make one of these? I mean, this isn't just sketching something out on a napkin, is it?
Far from it. The design and development of NSoC is an incredibly intricate, multidisciplinary effort. You need deep hardware and software engineering knowledge. It's highly structured, hierarchical, and maybe most importantly, it's an iterative process.
Iterative, meaning you go back and forth.
Exactly. It's not a straight line from A to Z. It's a journey of continuous refinement with feedback loops built in at every single stage.
Okay, so what are the big milestones then? The major steps along this journey?
We can break it down into several critical phases. First, specification. That's defining precisely what the chip needs to do, all the requirements.
Okay.
Then, architecture design, basically translating those requirements into a high-level blueprint. Next is design implementation. This is where the actual logic gets coded, followed by verification. Rigorously checking that logic does what it's supposed to.
A really important step, I imagine.
Crucial. Then comes fabrication, the physical manufacturing of the chip in a factory, a fab. And finally, validation, making absolutely sure the manufactured SoC works perfectly in the real world.
That iterative nature you mentioned, going back and forth. Why is that so critical? What happens if you mess up early on?
Well, this whole shift left idea, finding and fixing errors as early as possible, It's a strategic imperative. It's absolutely vital. Imagine finding a major bug after the silicon chip has been manufactured. We call that a respin.
Sounds expensive.
It is. It can easily cost tens of millions of dollars, cause product delays of months, leading to huge revenue losses. So that constant checking, those feedback loops, they're fundamental for quality and just managing risk, making sure the design is solid before it hits the factory floor.
Right. Let's dive into that first phase now. Specification. This is where you define the vision, like writing the mission statement for the chip.
Exactly. It's the genesis. You meticulously document all the requirements, hardware and software. This includes the functional needs, what the SO absolutely must do, like, say, process 4K video or manage specific wireless signals, and also the non-functional requirements, how fast it needs to be, how much power it can draw, how physically small it needs to end up.
And all the connections, too.
Yes, you describe all the internal and external interfaces, how it talks to the rest of the system.
So it sounds like a balancing act right from the start.
Yeah.
Like wanting maximum performance, but also needing super long battery life.
Yeah,
Those seem like they'd conflict.
precisely. That's a constant tension. Designers have to really understand the market needs, look at the competition, because, yeah, pushing for aggressive performance often conflicts with tight power budgets or wanting the smallest possible chip size. The detail and clarity here are vital. They set the foundation for everything that follows. The output, it's a detailed specification document.
Okay, got the spec doc. Then you move to architecture design. This is crafting the actual blueprint. You mentioned it's like being a city planner.
Yes, that's a pretty good analogy. You select the major functional blocks, the CPU cores, the GPU, memory controllers, maybe custom accelerators for AI tasks, and you define how they're all interconnected, how they'll communicate with each other. A really critical activity here is partitioning the design, deciding what functions will be done by dedicated hardware circuits versus what will be handled by software running on the processors.
Ah, the hardware-software split.
Exactly. And we also develop high-level models at this stage, sort of abstract simulations to check the overall behavior before we get into the nitty-gritty logic details.
You mentioned that synergy earlier, size, power, performance. I feel like I've heard an acronym for that. PPA. Is this where that really comes into play?
Ah, yes, PPA, power, performance, and area. You've got it. This trio represents the absolute central optimization challenge in SoC design, and it's not something you decide once. It's a continuous balancing act that affects every single phase that comes after this.
So trade-offs everywhere.
Constantly. For instance, if you prioritize maximum performance, you'll often end up with a larger silicon area, which costs more to make, and it'll probably consume more power, creating heat issues.
And the opposite. If you need really low power.
Right. If you have very strict power budgets, that might limit the peak performance you can achieve. This PPA trade-off directly influences everything from how the chip is physically laid out to, ultimately, the battery life of the device you, the listener, hold in your hand.
And you also mentioned IP reuse. What's IP in this context? Is like intellectual property?
Exactly. Integrating pre-designed and pre-verified intellectual property, or IP, cores is fundamental to modern SoC design. Think of IP blocks as pre-built, proven modules, like having a ready-made high-performance engine or a tested memory controller that you can just license and drop into your design.
So you don't have to reinvent the wheel every time.
Precisely. These blocks drastically speed up the design process, they reduce risk because you're using components that are already known to work, and they hugely improve engineering productivity. The key deliverables from this architecture phase are a comprehensive system architecture document and those high-level models we talked about, which guide the next implementation steps.
Okay, blueprint is drafted. Now we build the logic. Tell us about this front-end hardware development part.
Right, so the front end focuses on the logical design before we worry about the physical chip layout. It often starts with high-level modeling, creating abstract descriptions of algorithms, maybe in languages like C or System C. This lets designers rapidly explore different architectural ideas and check the overall system functionality works without getting bogged down in the details of specific logic gates yet.
Kind of like a sketch before the detailed painting.
That's a good way to put it. And it's often technology independent at this stage, which is great for reusing designs later.
And from that high-level model, you move to RTL design. What's RTL stand for again, and what happens there?
Yes. Next is register transfer level, RTL design. RTL is where the hardware's actual behavior is described using special hardware description languages, or HDLs, like Verilog or VHDL. At this level, you're specifying what the circuit does functionally and, crucially, how data moves between storage elements registers, which will eventually become physical memory units, flip-flops, and logic blocks on the silicon.
So it's getting much more concrete.
Much more. Modularity, breaking the design into manageable pieces and using strict coding standards are really important here, as is using synchronous design principles, making sure everything operates in sync with a common clock signal. That helps manage timing and prevent a lot of potential problems down the line. The main output here is the actual RTL code.
Now, this next part sounds critical. You said earlier it can take up, what, 50–60% of the entire development time? Functional verification. Why is it such a beast?
It is. It's absolutely massive because it's all about rigorously ensuring that the RTL code we just wrote accurately implements the functionality we defined way back in the specification. Finding bugs early at the RTL stage is paramount. Why? Because fixing an error in code is vastly, vastly cheaper and faster than finding it after you've already manufactured thousands or millions of physical chips.
So you test it to death, basically.
Pretty much. We create really comprehensive test benches and test suites. These are specialized pieces of code designed to drive inputs into our RTL design and check if the outputs match what we expect. We try to simulate every possible scenario, every edge case, to try and break the design.
How do you do that? Just run simulations over and over?
The simulation is a big part of it, yes. Running the RTL code in specialized software tools to observe its behavior over simulated time. It's got a very detailed virtual test drive.
Okay.
But we also use other techniques. Formal verification is one. This uses mathematical methods to actually prove that the design meets certain properties or can never enter an unwanted state. It's very powerful for certain kinds of checks.
Math proofs on the hardware design. Cool.
Yeah. And for the really big, complex SoCs, software simulation can be too slow. So we use hardware-assisted verification. That includes things like emulation, where we use special, expensive hardware machines that can run the RTL design much, much faster than software simulation.
Like a super fast simulator.
Kind of. Or FPGA prototyping. We actually map the design onto field programmable gate arrays reconfigurable chips to create a high-speed hardware prototype we can test with real software much earlier.
Right, FPGAs.
These techniques let us find bugs faster and test more thoroughly.
And you mentioned sneaky issues, glitches and hazards. Sounds like digital gremlins. What are those?
They can certainly feel like gremlins sometimes. Yes, glitches and hazards are basically temporary, unwanted signal fluctuations in the circuit. A glitch, for example, is like a brief, unexpected spike or dip on a signal line, even when that line's output should be stable, either high or low.
What causes that?
The main culprit. Finite propagation delays. Every single logic gate, every wire in the circuit takes a tiny amount of time for a signal to pass through it. It's not instantaneous. So if signals take different paths through the logic to reach the same point, they might arrive at slightly different times. That timing difference can cause the output to momentarily flicker to an incorrect state before it settles down.
Okay, so tiny delays causing temporary errors.
Huh.
And these aren't just theoretical annoyances. They cause real problems.
Oh, absolutely real problems. They can cause downstream logic, like memory elements or flip-flops, to capture the wrong value, leading to incorrect calculations or the system getting into a bad state.
Yikes.
They also increase power consumption because of all that extra unintended switching activity. And maybe most critically, they seriously reduce the overall reliability of the system. They can cause intermittent faults, bugs that appear randomly and are incredibly hard to track down, data corruption, even complete system crashes.
Which is obviously catastrophic in things like cars or medical devices.
Exactly. Safety-critical applications cannot tolerate this. These timing issues can also trigger a weird state called metastability, where a flip-flop's output gets stuck in an undefined, unstable state for an unpredictable amount of time. Basically, it can't decide if it's a 0 or a 1.
Wow. So how on earth do you find these things? They sound incredibly subtle and hard to catch.
It takes a combination of approaches. We can use graphical methods like Karnaugh maps during design to visually spot potential static hazards in simpler logic. We analyze the Boolean logic mathematically. We use timing diagrams to visualize how signals change over time. And critically, we rely heavily on sophisticated EDA simulation tools. These simulators can model propagation delays and flag potential glitches and hazards.
So the software tools help find them.
Yes, and static timing analysis, STA tools, are key too. They don't simulate the function, but they mathematically analyze all the signal paths in the design to check if timing constraints are met, flagging paths that are too fast or too slow, which can indicate hazard risks.
Okay, so you find a potential glitch or hazard. How do you fix it?
One of the most common techniques, especially for static hazards, is to add what's called redundant logic, often specifically a consensus term. Basically, you strategically add an extra logic gate or path to the circuit. This extra path is designed to hold the output steady during the problematic input transition where the glitch might occur.
So you're adding like a backup path to keep things stable.
That's a great way to think about it. It ensures the output stays correct, even if different signal paths have slightly different delays. It engineers robustness right into the logic.
Clever. Are there other ways?
Yes, sticking to strict synchronous design principles helps immensely. By using a clock to control when all signals change and are captured, you ensure you're only looking at signals after they've had time to settle down from any potential glitches. We also try path balancing, trying to make the delay through different logic paths more equal. And sometimes techniques like pipelining, breaking long logic chains into smaller clock stages, can help mitigate timing issues. But the key takeaway here, for you the listener, is understanding that propagation delay, the time it takes signals to travel, is fundamental. It's the root cause of almost all these tricky timing issues. A circuit can be logically perfect on paper, but fail in reality because of these delays.
Really fascinating stuff. Okay, so while all this incredibly detailed hardware verification is happening, what's going on with the software side? Is that developed later?
No, it happens in parallel. That hardware-software co-design approach is absolutely crucial for SoCs. You start developing the low-level software things like device drivers, firmware, maybe even the operating system kernel very early on. Often you use those abstract hardware models or emulators or FPGA prototypes we talked about, even before you have the physical silicon chip.
So software development gets a head start.
Exactly. It allows for early software testing, debugging, finding integration issues sooner, ensuring that the hardware and software will actually work together seamlessly when the real chip arrives. We shift left the software development too, just like the hardware verification.
Makes sense. Okay, so we've designed the logic. We've verified it as much as possible. Now it's time to turn that code into an actual physical chip layout, the back-end design.
That's the next major stage. And the first step in this back-end phase is logic synthesis. This is where automated EDA tools take the RTL code we wrote and transform it into a gate-level netlist.
A netlist? What's that?
It's basically a detailed description of the circuit in terms of specific logic gates, A and D gates or R gates, flip-flops from a particular manufacturer's library, and how they're all connected. It's the bridge from abstract behavior to physical implementation.
And I bet PPA power, performance, area is still a huge concern here during synthesis.
Oh, absolutely. The synthesis tools work hard to optimize that gate-level netlist based on the PPA constraints we give them, trying to make it fast, low power, and small. This is also typically where design for testability, DFT logic, gets inserted. Special circuits added purely to make it easier to test the chip after it's manufactured.
Planning ahead for testing.
Exactly. The output of synthesis is that synthesized gate-level netlist.
From that netlist, you go to physical layout. You called it building a miniature city on the chip earlier.
It really feels like that sometimes. It starts with floor planning, that's the high-level layout, deciding where the major functional blocks will sit on the silicon die, where the input-output pads go, and crucially planning out the power grid, how power and ground will be distributed across the entire chip.
Like planning the main roads and neighborhoods.
Exactly. Then comes placement, or logic placement. This is where the tools position all the millions of tiny standard cells, those individual logic gates, within the areas defined by the floor plan. The goal is usually to minimize the wire length needed to connect them, which helps with timing and power.
And the clock. That heartbeat signal needs special handling, right?
Definitely. Clock tree synthesis, CTS, is a dedicated step to build the network that distributes the clock signal. It's absolutely critical to deliver that clock signal to every single clocked element on the chip at almost exactly the same time, with minimal variations called skew and jitter. This is vital for the chip to operate correctly at high speeds.
So a very precise distribution network.
Extremely precise. And finally, after placement and CTS comes routing. This is where the tools physically draw the tiny metal wires, usually on multiple layers, to connect all the pins of the placed cells and blocks according to the netlist, following very strict manufacturing design rules, of course.
Connecting everything up like the plumbing and wiring in the city.
That's a good analogy.
Okay, everything's placed, the clock tree is built, all the wires are routed. You must check the timing again now.
Yes, absolutely. Static timing analysis, STA, is run again, this time on the fully routed design. It uses the actual extracted wire delays from the layout, so it's much more accurate. It mathematically calculates the signal delays along every single path and checks for any violations of timing constraints, like setup time and hold time for the flip-flops.
This is like the final check to guarantee it'll run at the target speed.
Essentially, yes. It guarantees the design's performance at its specified operating frequency, making sure all signals get where they need to go exactly when they need to.
And then, the final hurdle before sending it off to be made.
That's physical verification and sign-off. This is a whole suite of final checks, things like design rule check, DRC, which ensures the layout doesn't violate any of the incredibly complex rules required by the semiconductor foundry for manufacturing, like minimum wire spacing, width, layer overlaps.
Making sure it can actually be built.
Exactly. And layout versus schematic, LVS check. This confirms that the physical layout corresponds exactly to the original gate-level netlist, ensuring functional equivalence. No accidental changes crept in.
The ultimate double check.
Right. It's the final stamp of approval, the sign-off, ensuring the design is manufacturable and functionally correct before it goes out the door. The culmination of all this back-end work is the GDSII, or OASIS file. That's the final database, the blueprint, that gets sent to the semiconductor foundry.
Wow. So from that digital file, it finally moves into the physical world. How does the actual fabrication happen?
Right. That GDSII file goes to a highly specialized semiconductor fabrication plant, what we call a fab, or foundry. The manufacturing process itself is incredibly complex. It involves wafer fabrication, which is a sequence of maybe hundreds of steps involving photolithography, using light to pattern layers, etching, deposition, building up the layers of transistors and wires on a large silicon wafer.
All in an ultra-clean environment, right?
Right. Oh, unbelievably clean. Cleaner than an operating room by orders of magnitude. Any tiny dust particle can ruin a chip. After the wafer is fully processed, the individual chips, or dies, are tested right there on the wafer, then cut apart. Then they go through packaging, where the fragile silicon die is enclosed in a protective casing with electrical connections, the pins or balls you see on the outside of chips, so it can be soldered onto a circuit board.
And they probably test them again after packaging?
Yes, there's usually another round of testing after packaging to make sure the die wasn't damaged during assembly and the connections are good.
Okay, so you finally have the physical packaged chip back from the fab in your hand. But the journey, the work, it isn't over yet, is it? Getting the chip back is just the start of its real-world test. Now you have to make absolutely sure it works in a real system. That's post-silicon validation.
Exactly. This is the final and absolutely crucial stage, post-silicon validation. Now we take that manufactured chip, put it into a real test board, often resembling the final product's environment, and we run actual software on it. It involves complex co-validation testing, the hardware, the software, the interactions with peripherals, everything working together, ensuring all those processors, memory controllers, interfaces are behaving as expected.
What are you specifically checking for here? Is it just running the same verification tests again, but on real hardware?
Some tests might be similar, but the focus shifts. We're ensuring functional correctness under real operating conditions. We're verifying it meets the power consumption and performance targets for the specific ways the end product will be used, the target use cases. We check its tolerance to electrical noise, its robustness against temperature changes, voltage variations, things that are hard to model perfectly in simulation.
And the big advantage is speed, right?
Yeah. Yes, a key advantage is running tests at real system speeds, often gigahertz frequencies. This provides a much faster and more realistic assessment than pre-silicon simulation or emulation could ever achieve.
But debugging must be harder. You can't just look inside the code anymore.
Exactly. Debugging a physical chip is considerably more challenging than debugging a software model or RTL code. Visibility into the chip's internal state is much more limited. You rely on specialized test equipment and debug interfaces.
And the ultimate goal of all this post-silicon work?
The ultimate goal is to deliver validated SoC devices, chips that are confirmed to be fully functional, meeting all specifications, and ready for mass production and deployment in the final end products, whether that's the next generation smartphone, a critical automotive control system, or a powerful server. Getting these validated chips out reliably and often under very tight schedules to meet market windows.
What an incredible journey, from just a concept, an idea on paper, all the way through detailed specification, architecture design, that intense hardware and software development and verification, then the physical design, the fabrication, and finally, the real-world validation. You, our listener, hopefully now have a much deeper appreciation for this silicon symphony, as we called it, that powers just about everything electronic around us.
Indeed. And you can see how indispensable SoCs have become. It's their unique ability to achieve that synergy, miniaturization, power efficiency, high performance by packing everything onto one chip. And hopefully it's clearer now for you how that constant balancing act of power, performance, and area PPA is really the core challenge, the central optimization problem that defines the success of these incredibly complex devices.
And that whole shift left philosophy. Catching those errors early, especially those sneaky glitches and hazards caused by unavoidable propagation delays, it's absolutely critical. It's what saves companies potentially millions, maybe billions, and gets the tech you love into your hands faster and more reliably.
Yeah, the mastery of the entire sauce design flow, it's really a testament to this amazing interplay of deep theoretical understanding, very advanced engineering methodologies, and incredibly powerful electronic design automation tools that make it all possible.
So what does this all mean for you? Well, every time you seamlessly swipe on your phone screen, or your car's navigation system gives you instant directions, or your smartwatch tracks your workout, know that it's all built on this incredibly complex, iterative, highly optimized process we just walked through. It's all this hidden complexity that unlocks our modern technological world. So here's something to think about. With this relentless drive to integrate even more power and capability into ever smaller packages, what new possibilities might this unlock next? What happens when we can put even more intelligence everywhere? We'd love for you to mull on that.